Okay, Assalamualaikum warahmatullahi wabarakatuh. This is Statics, Chapter 5. This is the ending of Chapter 5, Section 5.5 until 5.7, right? So in Chapter 5, what we have covered is the concept of equilibrium of a rigid body, and then the free body diagram, how to deal with different type of support reactions to draw the free body diagram. We also have touched on also the two force member, and then we have also touched on how to solve using equation of equilibrium in 2D problems. And today for this particular recording, this is for three-dimensional problems, 3D free body diagram, equilibrium equation, and also solving 3D problems, right? So let's get straight into it. Bismillahirrahmanirrahim. Rabbi zidni ilma warzuqni fahma. Allahumma aftah lana hikmataka wa anshur alana min khazin rahmatika ya arhamar rahimin. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Bismillah. Alright. So by now, the concept of free body diagram, the concept of equilibrium, equation of summation of forces equal to 0, summation of moment equal to 0, and also solving throughout until you get the forces that is required. I think we have covered all of this, and the concept should be clear by now, right? If it haven't, it's not clear, please watch the previous recording first, right? Because now there's no new concept really. It's just that the problem in 3D will have its own complexities in terms of one, drawing the free body diagram and dealing with supports and support reaction in 3D, right? And also the number of equation will be more in terms of equation of equilibrium, right? In 2D we only have summation of fx and summation of fy. In 3D we have fx, fy, and fz. And in terms of moment, in 2D we only have summation of moment because it's just clockwise or counterclockwise. But in 3D we have moment about this axis, and that axis, right? So that's where it is different, but the concept is the same, right? So we go through the slides. You can go to the slide 5.5 to 5.7, and yeah, in terms of the application, you can see the slide. There are some pictures put in there in terms of some example of different type of supports that exist in real engineering application, right? So how you have ball and socket, you have a journal bearing. Hopefully you can imagine what's going on in this type of supports, right? Because if you cannot even imagine what it is, it's hard to then relate to what we are drawing in a free body diagram, right? So I'm going to try my best to explain what's going on with this type of supports. But if you have never seen it before, it's going to be quite difficult, right? But hopefully it's okay, right? Now, so there are different type of support that are being shown in the slides, right? So one is just smooth surface support, right? So basically this is if you have a surface and then you have for example the leg of a chair is just sitting there, right? So the concept is exactly just what we have discussed in 2D, right? If you have something like this, the only restriction is, okay, the question that you have to ask is what movement and what rotation does the support restrict, and what the movement and rotation that it does not restrict, it allows. You can freely move or rotate in that way, right? So in that case, if this is the leg of something, of a chair for example, then it is a member sitting on the ground. So the only restriction, because right now we haven't covered friction yet, because if you have a friction then you have this friction, but now assuming no friction, the only restriction is going down, right? It cannot go down, right? It cannot go down. If there's no ground there, it will just go down, but this one prevents it from going down, hence it stays there, it is static, right? So in that case, the free body diagram, when we draw, we just draw the force upward. Why? The ground is the one that is providing the supporting force so that it maintains in place, right? You do not draw anything else because there's no other restriction, right? So the question, like to reiterate, the question is, does this support prevent from vertical movement, horizontal movement, and of course in 3D you have the three axes, right? This movement, and this movement, right? The only restriction is going down, right? And then does it restrict any rotation about this axis, and this axis, right? The three axes. So in this support, it doesn't restrict any axis, right? And then you have ball and socket, right? Ball and socket is, what are the example? If this is quite an old example, but hopefully you still have seen something like this, right? If for example there's like a souvenir pad where you have some paper and then you have like a pen, and then it is the case of the pen is attached to the pad, where it's basically you can rotate the pen, right? But it's there, right? So if you can imagine, inside it's basically a ball and then a socket capturing it, right? So you can actually rotate all you want, but the ball itself cannot move in any axis, right? It's captured there. But this one can, if I'm using this one, it can rotate any which way, right? So if you have seen that one, you can imagine, right? That's an example of ball and socket. Another example, I think some people mention about the console, like if you have a game console where the joystick or joypad, whatever you call that, some button you can just rotate all the way, but meaning it's inside it's like a ball socket, right? And you can rotate this thing, right? So that's an example. Hopefully you can imagine by now. So in that case, right, the question is, does it restrict any movement? So actually you cannot move in this vertical, horizontal, right? Okay. If I assume this is X, Y, and Z, right? So that ball and socket, does it restrict any X-axis movement? Yes, it does. Any Y movement, it restricts also. Any Z movement, it restricts. Basically, it restricts all three axes. So when you draw the Freebody diagram, you have to draw the X component, Y component, and Z component of support reaction, right? And then, does it restrict any moment? Does it restrict rotation about X-axis, about Y-axis, and about Z-axis, right? Does it restrict any moment? So you can rotate all you want, so it does not restrict any moment, right? Hence, when you draw the Freebody diagram, right, in terms of the 3D, basically you just have all the three support reaction, right? In the X-axis, Y-axis, and Z-axis, right? So that's how you draw the Freebody diagram, right? And then you have, for example, journal bearing. Journal bearing is where you have basically like a bearing where, for example, you have a rod, in this case, from here basically it's captured in this like casing there, where from this side like this, right? So it can rotate, right? It can rotate about this axis, right? I'm not sure if I rotate, you cannot see, but it can rotate about this one, and it can actually move in this direction, right? This direction it can move, right? So if you can imagine that, right? So if which is normally the x-axis, okay, let's consider it's like this, right? So this is the x-axis, y-axis, and z-axis, right? So the question is, does it prevent any movement in this x-axis? Yes, it does, right? You cannot move this in that way because this is captured, right? You cannot move that way, right? But this is the x-axis, so you will have the reaction in x-axis. Does it restrict any movement in y-axis? So you do not, right? It can move, right? So there's no restriction there, so you do not draw any force there. Does it restrict from z-axis? Yes, it does. You cannot move, right? So you have also z force, right? So you have force in x and force in z in terms of the support action. Now, in terms of moment, does it restrict any moment about x-axis, right? Rotating like this about x-axis. Does it restrict? Of course, you cannot rotate, right? You cannot rotate this way because it's like this. So you have also mx there, right? Does it prevent any rotation about y-axis? No, right? You can actually rotate this way freely, right? So you do not have any support moment there. Does it restrict moment about z-axis? Can it rotate this way or not? It cannot, right? You cannot rotate this way because it's captured like that, right? So in the end, you will have, if you okay, where is the x? So it depends on the way you draw and where is the x, right? So in this case, if you imagine it to be this way, right? When you draw the Freebody diagram, of course you take out the casing there, right? So basically, if you have this is x-axis, y-axis, and z-axis, right? So again, does it prevent any movement in x? Yes, it does. So we have also here, let's say this is point A, right? So you have ax there. Does it prevent any movement y? No, it does not. So you do not have any force. Does it prevent any movement in z? It does. So you have az. Now, does it prevent any rotation about x? Yes, it does. So you have max. Does it prevent any movement in y? It does not. Does it prevent any rotation? Sorry, rotation about z? Yes, it does. So you have maz. Right. So that will be the Freebody diagram of a journal bearing. Right. Now, later or in your book, you can see that there are something that is drawn. If we are drawing the diagram, can I draw it here? So in terms of the drawing, right, it will be something like this, and then this is the casing, basically, right? Something like this, and then that's the continuation of the rod, right? So something like this, right? And you can imagine this one, right? This is the rod, and that is the casing, right? So is it clear there? All right. Now, you have journal bearing. Right, and you have also another one is, what is it? Okay, I don't have truss bearing. Right. The truss bearing. If I'm not mistaken, let me check. I forgot to. Yeah, it's truss bearing. I forgot to bring my textbook while I'm recording this, unfortunately. So, but yes, I remember it correctly. One is journal bearing, one is truss bearing. Now, the drawing is exactly the same. If you see, it's exactly like that, right? However, the name makes a difference. Where journal bearing, this one is you can freely move, right? The mechanism is the rod can move in this axis, but truss bearing, you cannot. It is stuck. You cannot move this way. You have the drawing is the same, exactly the same, but the name is different, implying the mechanism is different, right? So in truss bearing, so I'll draw with a different. In truss bearing, right? Hopefully you can understand it. In truss bearing, you cannot move in this axis. Hence, you will have a y. Right? So make sure you understand this correctly. When you have journal bearing, you only have ax, max, az, maz. Okay, do not memorize this. Do not memorize ax, az, etc. Because x, y, z, it depends on where is the axis and where is the rod. If the rod is in the x-axis or y-axis or z-axis, then it's different, right? But you have to understand where it can rotate, where it can move, where it cannot rotate, where it cannot move, right? So you have to understand that way. The point here is, for journal bearing, the mechanism allow for this rotation, movement, that movement along the axis, it is allowed. Hence, you do not have AY because there's no restriction in that movement. But in truss bearing, it restricts that movement, so you have also AY. Alright, so hopefully that's clear. If it's not clear, please comment down below. State what is not clear, why is it not clear, and if it is clear, then it's okay. Of course, if still not clear, you also can ask in the class, right? But if you are afraid you will forget in the class, etc., just write down there so that I can know what is the question. Alright, another thing. From the drawing, you can see that the rod is actually round, right? Hence, obviously it can rotate. But it can be also, be it journal bearing or truss bearing, but the rod is different. The rod is, that's why it's square like this. Right, the casing there, something there, and then it's continuation there, right? Something like that. My drawing is so bad, but unfortunately, but you get the idea, right? Meaning that the rod itself is a square, shape. So the implication is what? When it is a square shape, if let's say it's a general bearing, a square shape, so general bearing you can slide this way, but because it's square, you cannot rotate, right? So in that case, if you have the Freebody diagram, right, where it's a square rod, so you have also AX and then MAX, AZ, MAZ. This is all the same because the same argument and the same question is the same, right? Meaning that can you move that way, can you rotate that way, it's the same, right? However, the additional point is this, MAY, right? Because it will also be restricted from rotating about that axis. In this case, about y-axis, right? It cannot rotate about y-axis, hence there's a restriction, hence you have the support reaction moment, right? So this is MAY. Of course, if it's a thrust bearing, then you have also AY. I'm drawing here if it is a general bearing, where it is free to move in y-axis, but it just cannot rotate. Why? Because of the shape, which is square, right? So make sure you understand all of this, because you can memorize, right? You can memorize, but I think that's not a good strategy. The good strategy is you understand, so that you can see and ask yourself every time, can it move it this way? Can you rotate in this way logically? And from there you can draw the correct Freebody diagram. And remember, the Freebody diagram should be drawn correctly because it's the first step in a normally long calculation. If the first step is wrong, your Freebody diagram is wrong, when you do the equation afterwards, it will be affected by whatever you draw, right? If you're missing something, miss some force, miss a moment, obviously it will affect the whole calculation, and that is not what you want, right? So if you have any doubt and question about Freebody diagram, please do ask. Do not assume, right? Please do ask. All right, so that's about bearing, and also we have hinge. How to understand hinge? You can understand the door. Okay, I'll just show the door, right? Not to ask you out, right? But so there's a door there, and let's see, can we see any hinge there? Okay, in this case, okay, the focus is out of focus or something, right? Can you see this one, right? Okay, this is a hinge. Can you see this one? Is it clear? Let me see in the, yeah, oh, sorry, that's my forehead. Alright, this is a hinge, right? Meaning that, so from here you should be able to tell what is allowed and what is not allowed, right? So the door itself, you know how it works, right? So you can see that actually, if I assume, okay, I have to bring myself down here. If I assume this is my x-axis, y-axis and z-axis, right? X, Y, Z, right? So this hinge actually prevent any movement, right? You cannot, this door cannot be moved that way, this way, or upwards. It cannot, right? So when you draw the Freebody diagram, you'll have AX if this is point E, AX, AY, AZ. Hopefully you understand that. What about the rotation? Does it allow or restrict rotation about X? Can you rotate this way? Right? Can you rotate the door this way? You cannot, right? So you'll have MAX. It cannot rotate that way. Does it rotate or allow rotation about M or Y? Can you rotate it this way? You know, that way, about this axis? You cannot also, right? The only rotation that you can have is this way, right? Oops, this way. Meaning that it can rotate about Z. You can rotate that way, right? You can rotate this way. So the only allowed rotation, okay, back here. Oops, sorry. Okay, we're back. So back to the hinge. The only movement that is allowed is rotation by z-axis, right? This rotation. So meaning that when you draw it, so if I am to draw the door, how to draw the door? Let's say the door is something like, if I'm just taking that one, right? And if I assume that one is on x-axis, right? So the door is something like this. That way where the axis is x is here, y is here, z is there, right? Is it clear in the okay? Hopefully that's clear. The door and x-axis is there, y, z, right? So as we mentioned and as we discussed, it will have all the three forces. So let's say this is point A. Okay, let's use a different point. Let's say that's point B, right? This is point B. So you have bx, by, bz, right? And then also you'll have a restriction here, m, bx, m, by. And mbz is not there because it does allow rotation about z. It does not restrict rotation about z, hence there's no support action in that axis. But hence your Freebody diagram at that point is this thing, right? Of course, if you have 3 hinges, then you have 3 repetition of that, right? Hopefully you understand the explanation there. Now, before I forgot, there's one point that I should make. If you notice how we draw the moment, right? This moment. You have to draw both the thumb and your fingers, if you understand what I mean. Because in the right hand rule, in terms of the understanding, we have discussed this before, I think, in terms of the understanding of moment, this is actually the rotation, right? So for example, if I have x, y, and z, so if the rotation is I, right, the vector I, in the direction I, meaning it's your thumb is in this direction, in the x direction, positive x, and then as you can see the rotation here, it will be counterclockwise, right? Counterclockwise from your perspective. In terms of myself, this is counterclockwise, right? My hand is, okay, this is counterclockwise, right? So if your thumb is minus I, where this is x, right? So plus I, minus I, right? So if minus I, you can see that it is clockwise. Similarly, if positive j, because x, I, j, k, right? Positive j from this perspective is counterclockwise, and if negative j is clockwise, right? Similarly, k, positive k, if you look from up, is counterclockwise, negative is clockwise, right? So that's what you mean by this is the actual rotation. Like the door here, K, but the rotation is this way, right? Meaning the door is actually rotating this way, the finger there, this way, right? So we have to draw both, meaning the thumb and the finger. Meaning this is the thumb, this is the finger. This is the thumb, this is the finger. What I mean is, you cannot occupy. For example, I cannot draw like this. For example, if I have AX here, where you have the force reaction, and then suddenly for the moment you just occupy it here, MAX, right? Because no, that line there is for the force. For the moment you have to hold your own thumb, right? So it's here, right? Hence the drawing is you have to separate for force and moment, right? So if you occupy like this, for example, the moment actually occupy the force, the drawing, the Freebody diagram is wrong, right? So make sure you understand that. All right. What else? So if you have fixed support is easiest, right? Easiest meaning that if you this subfix, you glue it somewhere or it's cemented somewhere. So obviously it cannot move in any axis, it cannot rotate about any axis. Hence you will have AX, AY, AZ, MAX, MAY, MAZ, for example, right? So I'm just showing here just to make it clear that, for example, when you say A, B, etc., that's because that is point A, that's point B, etc., right? So because some students actually they do not know why the notation is like that, right? It's not always A, it's not always F. We name it based on certain things, right? Hopefully you can see. Alright, so the idea is, if you can go back to the slide, the idea is, as a general rule, if a support prevents translation of a body, so you have a force opposite of that direction. if it prevent rotation about any axis, then you'll have a moment exerted in the opposite way, right? And of course, as we mentioned before, right? For example, for smooth surface support, right? For example, like this, right? Sorry, like this way, right? So when you draw a force like this, right, obviously confirm the force will be going up because the surface only prevent from downward movement, hence it gives you the force upward. However, for this thing, general bearing, hinge, etc., the direction that you give is for the most part assumption, right? Because it restricts both, right? When you have general bearing like this, it restricts both that direction or this direction, right? It restricts both. So when you draw in assumption direction, and if it's negative, it's just the opposite. And my suggestion is always draw everything in the positive direction. Assume everything positive. For example, like this. Because this is positive x, positive y, positive z, right? So I always draw ax, ay, az in the positive direction, so that when I calculate until the end, if it's negative, then I know for sure it's in a negative direction. If you draw in a mixed way, for ax you draw backward there, for ay is positive here, for az suddenly downward, then when you get negative, it's quite confusing. Is it upward and downward, or etc.? And you have to check back again, right? So it's easier, making it life easy for you to check in the exam especially, and also for the examiner, assume everything in positive direction, so that whenever you get a negative value, you get actually a negative I or negative J or a negative K direction, right? That's easier for you and examiner. Do not make the examiner head confused and tension, etc., because it might affect your mark anyway, right? So that's a suggestion. Similarly, as you can see, I draw everything in a positive direction. Dx, dy, bz, and dx and dy. There's no bz there. Alright, so that's the concept. So we'll go for some example, I believe. Alright, important note before we go some example. A single bearing or hinge can prevent rotation by providing a resistive coupled moment. However, it's usually preferred to use two or more properly aligned bearing and hinge. In these cases, only force reaction are generated and no moment reaction are created. Now, how to explain this? Because this requires you to understand certain things in terms of the effect of the structure, right? And if you are designing something and if you want to calculate something, this is quite an important concept to understand. However, in terms of the exam, I personally, and we know here in this university, I'm not sure if you are a student of other university and they use it differently, but here we always prevent from having this question in the exam, because it will not only test you on the general Freebody diagram, how to apply it and equation. It adds certain added understanding that you have to have. So we think that it's not that fair to test the student up to that level, especially this subject is taught in the first semester, in the first year, right? So yeah, so but if you want to understand this, please ask in the comment, of course, or in the class, right? In the classroom, if you are interested to understand this, we can discuss it in the class, right? So this is about properly aligned, and how and why. If you look at this structure, the moment reaction will not be drawn there, right? Because it's properly aligned. So the tendency for rotation is already taken care of. Okay, just a glimpse maybe. For example, like just now, right? If you have a bearing, it actually prevent this rotation, right? This is about x-axis. This rotation, right? This rotation is already prevented by this bearing. So you should draw MAX, for example, right? This one. However, sometimes in terms of the design, we put two bearing here or three bearing there, right? So that actually this two bearing, by preventing it here, it prevent this movement, right? In X. Here also it prevent this movement in X. Hence, by that prevention already, it already prevent from any of this rotation, because this one will not go there, this one will not also go in this way. So the prevention of this rotation is already taken care of by that force, not by moment, but by that force, right? Meaning both way restriction this movement. So there's no possibility of rotating here, here, right? Because which direction? Okay, it's easier in this way, right? Okay, so this bearing will already prevent it from going up and down. This one is also preventing it up and down. So both of these points will not go up and down. If you can imagine, if this one will never go up and down, at the middle here, it will never have to restrict this rotation. Even though this bearing can restrict this rotation, but by these two bearing, this bearing will not have ever to exert that moment. Hence, they say, okay, this is properly aligned, so you don't actually draw that mx, right? So that's basically the concept. If you understand, good for you. If you do not be afraid. We will not test you on that understanding for the exam purpose. But if you want, or if you will go into becoming engineer that will design all of this, maybe that is an interesting concept you need to understand. But because in this university, students that take this subject is from various faculty, right? From biotechnology, etc. So you might not need this type of understanding that much, right? So for the type of for the exam, again, we will not test you on this. If you are interested still, ask me in the class. All right. So that's about properly aligned and how it affects our drawing in Freebody diagram, right? All right. Then we go to equation of equilibrium. Of course, we have covered this one already. Basically, in terms of vector, it is summation of force to 0, summation of moment equal to 0, right? On that side there. Is it still in this frame? Yes. Of course, in terms of scalar, it will be summation of fx equal to 0, summation of fy equal to 0, summation of fz equal to 0. In terms of scalar also, the moment equation is mx equal to 0, summation of my equal to 0, summation of mz equal to 0. Right. Okay, so that's basically the equation of equilibrium there. And I think you understand that equation, right? This equation there. Alright, so I think now the interesting thing here, if you deal with 3D, right? The axis where about which you take the moment, for example mx, right? It does not necessarily be the x-axis, for example, right? Because this x-axis, y-axis, z-axis, right? So you have a structure there, right? So the moment here, you can take moment about x-axis or moment about meaning this moment, this rotation, or it's about something about here, right? Right. So how to say this? Because in 2D, you can take moment about point A or point B or point C, for example, right? So similarly, moment about an axis in 3D, you can take about this axis or this axis or this axis. It still rotate similarly, but about different axes where the distance will be different, right? So if you use R cross F, R will be different. And the selection can make the solution be easier. Hopefully we can have some exercise after this, depending on the type of structure, right? Hopefully when we go into the example, we will see this, right? Constraint and statical determinacy, right? So this is about redundant constraint and also statically indeterminate, right? So redundant constraint meaning that if you have, for example, two different constraints that is redundant. What do you mean by that? Meaning that, for example, if you have a structure, let's say a simple structure like this, and it is fixed here, right? It's cemented here, fixed, and then here you have a bearing here, right? For example, now fixed support actually prevent any movement and any rotation. It prevent all, right? And this one, bearing, it actually prevent this movement, but it allow this movement, and it rotate, it prevent also moment about this axis and this axis, but you can you can rotate about z axis, for example, right? But if you have both, it is actually redundant, because this type of movement, right, movement in x-axis is prevented already by this, and this one is also preventing it, meaning two different constraints prevent the same movement, for example. That's redundant, right? The same as movement, etc., and other rotation. So that is what it means by redundant. And normally in the real design, it's not a problem. Why? It's okay, it's redundant, right? More is better. But in terms of calculation, in terms of static calculation, that introduce more unknown than equation that we have. For example, here, that's why we have fixed support, right? If you draw the Freebody diagram, how many unknown do you have here? I'll let you think in 10 seconds. Right? Fixed support, how many number of unknown when you draw Freebody diagram here? Alright, it should be 6, right? Because we have x, y, z force. For example, this is point O, right? OX, OY, OZ, and also moment, right? MOX, MOY, and MOZ. It restricts all, because fixed, you cannot move, you cannot rotate. Now, you already have 6 here, and if you have any support elsewhere, right? Bearing here, etc., etc., and you will add another 4, etc., depending on whatever type of support there. However, how many equations do we have? We have 1, 2, 3, 4, 5, 6. Right? So that you can see that already 6 here and then 4 here, etc. It will be more than 6. So you cannot solve. That means it is statically indeterminate. Now, so normally in terms of calculation, in terms of exam, the calculation-based question, you will never have statically indeterminate, because we want you to solve. So we will give you the number of unknown is the amount that you can actually solve, which is 6 based on 6 equation here or less, right? However, there are some understanding question that normally is also asked in the exam. Sometimes they say, what if this support is changed into that support? What will happen? And some of the question actually imply that, oh, when you change to that support, the number of unknown will be more than 6. Hence, it is statically indeterminate. Hence, you cannot solve. Right? So that's example of, if you've seen the previous exam question, there are questions like that. Right? So yeah, what is this? Okay, that's why in the exam, in terms of calculation question, you actually almost never see fixed support, because fixed support you will have already 6 unknown here. Hence, to be able to solve the question, you cannot have any unknown elsewhere. You cannot have any other support. And normally, from the perspective of the lecturer, we want to test you with more than one support, right? Because it is more testing to the student whether they understand or not. Hence, that's why if you see the previous exam, very rarely you will see fixed support, because if the question gives you fixed support, you only have one support to be tested on, right? But if you have, for example, bearing here and then ball and socket here, etc., then you have 2 here, 3 here, etc., etc., and the total should be 6, right? So we can test you in more support, right? So that's normally what happens. When I say normally, it can suddenly this lecturer just want to put it fixed support. That should be easy normally, because you only have one point to consider and all the forces and moments, right? But I'll just explain here to see that why certain things is not in the exam normally, right? So right. So in this part, the understanding is just this. Make sure you understand that the number of unknown, if it's more than the number of equation, which is 6 in 3D, then it is statically indeterminate. So make sure you are familiar with that phrase, because like just now I mentioned, if the question in the exam says, normally, for example, if you have ball and socket here, which is 3 force, right? X, Y, Z, and then you have another, I don't know, something else, and in total is 6, right? Here is bearing, for example, right? When the question says, what is this ball and socket, is changed to fixed. So meaning that, okay, you have to understand, okay, when this change from ball socket to fixed, so it changed from 3 unknown to 6 unknown here, and added to the other unknown, the number of unknown is more, hence you can use that phrase. Now it is statically indeterminate, meaning you cannot determine the force using statics, because in using statics we only have this equation here, and hence you cannot solve, right? So that's an understanding question that can be asked in the exam. Alright. Improper constraint, right? This is another concept, improper constraint, meaning that the constraint is not proper. Right now, I think in the example, it gives you the example of if you have 2 ball and socket, right? For example, if you have this structure here, if you have ball and socket here, and ball and socket here, right? So ball and socket, how many unknown here? 3 seconds. How many unknown? You have AX, AY, AZ, right? It prevent all the movement, but it doesn't prevent rotation. How many here? Another 3, right? So in total you have 6 unknown. Can you solve? Based on number of equation, 6 unknown in total, 6 and 6 equation, you can actually solve. However, this is improper constraint, because why? Both sides, both ball and socket actually prevent any movement, so you cannot move. However, can you rotate? It can actually, right? Because this doesn't prevent any rotation, this does not prevent any rotation, so this actually can rotate. Hence, it's not proper, because this will not be confirmed to be static, right? Because it can actually have any rotation, for example, in this case, right? So that's an example of improper constraint, right? Even though the number of unknown is okay, it's within what we can solve, so it's not statically indeterminate. However, in reality, that's not a proper constraint, because it will not constrain the structure to be static, right? So yeah, so that's the concept of improper constraint. Yeah, the same is, I think the another example is 2D example, where you have a pin support here, and then you have a roller here, not down here but here, right? So this pin support actually prevent from moving up and moving horizontally, right? But you can rotate, right? It's like this, right? You can rotate, you just cannot move up horizontally here, right? And the roller, if you have roller here, right, then this will be static, because the rotation actually prevented by this roller. But if you have roller here, where the normal direction is this way, right, you cannot go into that way, right? However, this is not proper, because this will just go down, because nothing is preventing it from going down, right? So that's also a case for improper constraint, right? So that's basically the example shown in the slide, right? Alright, so we will go into some example. I'll just change the battery for the camera because it's dying, and we'll just go back straight into the example. Alright, so we have several examples that we will go through. This is basically from the slides. And yeah, if you normally if you are my student, you have the access to all the slides already. But in case if someone is watching this is not from the pool of my students, and you don't have the slide, because for 3D question, normally it's harder to actually for me to manually draw the question here, right? So what we will do is I'll just put on, normally I do not do this, right, in my recording, because it will actually add more work for me to edit the video, normally, because I have too much things to do. For this type of recording, I just record and then just upload, right? Record, just cut and upload, no more technical editing, sorry. But for this one, I'll make an exception, because it's quite difficult for me to draw, and it's important for you to see what is the question originally, right? For 2D I can still draw it, for 3D it's quite difficult. So what we'll do is I'll just put the picture here. Hopefully I remember before I upload it. So I'll put the picture here on the question, and hence you can take a look. Of course, when we will try to answer it, I'll just make it disappear, because I need all the space here, right? But first you can see, okay, so this is example 1, so hopefully the picture is somewhere here, right? And if you can see the picture, it's basically a rod that is like an L rod in a 3D space, and you have thrust bearing. If you okay, because I put the picture. However, the question I will read, because I don't think if I put also the wording of the question, it will take too much space. So I think the important thing is the diagram for you to see. So okay, the diagram is there. Hopefully I'll edit this one. So the question is, so I'll read it and hopefully you just note down if you need to. If you have already the slides, you have all of this anyway, right? So the rod supported by thrust bearing at A. So at A, if you see the diagram, you have a bearing there, right? It's just a bearing there. But as we mentioned earlier, there's two types of bearing: thrust bearing and journal bearing. Journal bearing, it does not restrict the movement in that axis, right? You can freely move. But thrust bearing, you cannot move. The mechanism prevents it, right? So in this question, the statement is thrust bearing. So bearing A is thrust bearing, right? And also, so the rod is restricted by or supported by two things. One is thrust bearing at A. Second is cable BC. So you can see that at the end there's a cable BC going up there, right? And also you have it is subjected to the force of 80 kilonewton downwards, right? So it is shown in the diagram. So that's basically the question. Given is thrust bearing at A, cable BC, and force 80 kilonewton downwards. And then you have the question is find the reaction at the thrust bearing A and also cable BC. So you have to find what is the support action at A and at point B, basically, right? From the cable BC and from the thrust bearing A, right? So just take a look at the picture. Try to imagine. This is my question to you before we answer the question calculation wise, right? How many unknown separation in total? How many? I give you 5 seconds. Right. It should be what? At the point B is just one, right? One force upward, which is from the cable. But at point A, how many do we have? Now, if it is thrust bearing, you will have all the three forces, right? AX, AY, AZ. And you will have two moments, right? MAX and MAZ, right? Hopefully you can imagine that. And the only freedom is MAY, right? Because it does not restrict the rotation there. So in total, how many you have? 5 plus 1, which is 6, right? So then we can solve, right? So hopefully before you even start, you can imagine the separation already. Hopefully. If you have any question, please do ask in the comment or in the class. Alright. So this is disappear now, the picture, and we'll just go and draw the Freebody diagram and solve, right? First we draw the axis. So let's say we have the x-axis here, y-axis, and z-axis there, right? And so we have the rod, the bent rod, right? So basically we'll just draw the rod itself, right? As we have mentioned before, free body diagram, the body should be free from the surrounding, including the bearing, including the cable, right? So we'll just draw the rod, something like that, right? So it is something like that, roughly. And we have the forces from the cable. So we have forces upward from the cable. Let's name it F, BC. We have forces downwards, which is 80 kilonewton there. And also we have the support action at point A. Is that point A there, right? So in that case, as we have mentioned, we have all the forces in all three components because it's a thrust bearing. It doesn't allow movement, including in the x-axis, right? So we'll have Ex. Let me draw it outside, right? So EY, EZ, right? So we have all the three forces as a support reaction, and also we have moment support reaction here, where this is MEX and EZ, right? So the only freedom is the rotation about y-axis, right? So here, right? So in the end, we have 5 unknown here and 1 unknown here, which makes it 6, and we can solve it because we have 6 equation of equilibrium, right? Is this a complete Freebody diagram? What is missing? Well, actually what is missing is the dimension, right? So we'll have to put on the dimension. So this is 1.5 meter, 1.5 meter, and 6 meters depth, right? So that's basically the Freebody diagram, right? Now, so as we mentioned before, right? So basically this is 6 unknown, we have 6 equation. However, the selection of which equation we solve first can determine whether it is going to be easy or difficult, right? So which equation should you use first, right? So now, among the thinking that you should be able to have is just to imagine if you apply any specific equation, what will be the implication, right? For example, if I say, can I do a summation of fx equal to 0? And how many unknown do I have? If there's only 1 unknown, then you can solve straight away. If there's more than 1 unknown, then might as well start with another equation, right? For example, so if I use summation of fx equal to 0, how many unknown do I have? I have this one and that one only, right? So in that case, that's very easy, right? It's straight away. If you do summation of fx equal to 0, you have ex equal to 0, right? That's the first answer already, right? Because what we need to solve in the end is support reaction at A and B, right? Meaning that all is 5 and then this 1, right? So we have already settled for 1. If you do summation of fy equal to 0, how many unknown? 1, and that's the only one. So we can already solve that one also, right? So we can do summation of fy equal to 0, ay equal to 0. So 2 down, 4 to go, right? What if I use summation of fz? How many unknown? So we have 1 and we have 2, right? So keep that aside for a while, right? Because if you write that, that's not a problem, but might as well we solve what we can straight away first, right? So you can do that in your mind first, right? Okay, that one keep aside first. Summation of summation of moment about x-axis. How many unknown? We have 1 and we have 2, right? You have to be able to imagine that this unknown actually produce a moment about x-axis, correct? Right? It rotates that way. So you have to unknown. So keep that aside for a second. What about moment about y-axis? How many unknown? There's only 1, right? Now, I think some of the students, they get confused between when we say moment max, maz with moment about x and moment about z, right? So this, make sure you understand the difference, right? One, when we say moment about x-axis, moment about z-axis, that is, we do the summation of all moment produced about that specific axis. For example, if you say moment about x-axis equal to 0, it means that if you add all of the moment about x-axis, it should be 0, including max, right? So meaning that moment about x-axis is produced by this moment itself. This force also produces a moment about x-axis. This force also produces a moment about x-axis. So hopefully you understand the distinguishing. You are able to distinguish between mx, which is moment about x-axis, and max, which is the support reaction about x-axis, right? So that's 2 different things. Hopefully you understand, right? If you don't, if my explanation is not clear, if something is not clear yet, please do ask that question also. All right. So again, what can we do just now? Okay, summation of mx, we have 2 unknown, 1, 2. Summation of my equal to 0, and we have 1, right? So we can do that. Summation of moment about y-axis equal to 0. We do not have may here, no problem. This one doesn't produce any moment about y-axis. This does produce any moment about y-axis, right? So normally we take counterclockwise as positive. In 3D, that's the convention, right? So, okay, let's start with FBC, right? FBC, hopefully you can imagine that it produces counterclockwise moment about y-axis, right? Hopefully you can imagine that. So that will be plus FBC times the distance of, this is the distance, perpendicular distance to the axis, right? So times 3. And then this 80 kN is producing moment clockwise about y-axis, right? So minus 80 times distance of 1.5 equal to 0, right? Because everything else doesn't produce any moment about y-axis. These are the only two forces that produce moment about y-axis. So from here you can solve that FBC will be 40 kilonewton, right? Right, I think 80 divided by 2 is 40 kilonewton. Obviously, this must be positive because this is tension of the cable, right? Now, after you have settled for this, actually you can go back to the equation that we have left behind just now, which is summation of Fz, right? Because right now, if we do summation of Fz equal to 0, before it's 1 unknown and 2 unknown, right? But this one is known already, so I can go back to summation of Fz equal to 0, then you have a Z minus 80 plus 40 equal to 0, and a Z equal to 40 kilonewton, right? Alright, what else? So 1, 2, 3, 4. We have another 2, right? We have done already summation of My. Right now, if this already is also found, we go back to summation of Mx, summation of moment about x-axis. So you only have one unknown left, right? Because this is already known, right? So summation of Mx equal to 0. So you have Max. All the rest doesn't produce any moment about x-axis. This FBC, right? It produces counterclockwise moment about x, so it's plus. FBC is 40. The distance is 6 meter. It's 6 meter, right? And then this 80 kilonewton is producing clockwise moment about x-axis, so you get minus 80. The distance of also 6 equal to 0. So Max equal to what do you get here? 40 times 6. 2240 kilonewton meter, right? Am I correct? Should I check? Because right, so Max becomes 240 kilonewton meter. That is correct. And the direction is, the assumed direction is correct, positive, right? As I mentioned before, I always assume everything is positive, so when I get a positive answer, it is in positive I direction. And then what else is left is summation of Mz equal to 0. So what we have, Maz, okay, no forces actually produce any moment about Z, so equal to 0 straight away, right? So that is your final answer. You have 1, 2, 3, 4, 5, 6 answers for 6 unknown, and you have solved them all, right? Anything not clear? Hopefully everything is clear. Is the zooming okay? Not the zooming, the what do you call that? Focusing, right? My camera unfortunately is focusing bizarrely on this one. Anyway, so hopefully this is one very easy example where the calculation is quite straightforward because everything is vertical, something like that, right? In some question it will be more complicated, where you might not be able to do using scalar computation. This is using scalar computation, right? Meaning that when you use scalar, it's just summation of force and summation of moment, which is summation of force times distance, right? FD. The only thing is you have to be able to visualize the rotation and also which force produce which moment about which axis, right? So if you do vector, then you straight away R cross F, and then you straight away get IJK, and then you just all the x component, y component, z component, you just bring to the equation and then you solve, right? You can also do that. The answer should be the same, right? You can try. So which method with its scalar or vector is easier? Actually, it depends to the student, right? Each student have different way of thinking. Actually, if you can understand the scalar, this one is quite straightforward for this particular question. All right. So let's take a look at another question. So this is the next question, example number 2 in the slide. Of course, as before, I'll just put the picture here, somewhere here, and yeah, I'll just erase this, and you can just look at the picture for a second. Alright, so have you looked at it? Okay, so in this example, the question is, basically you are given the uniform plate. So that plate is uniform, meaning that the weight distribution is the same, meaning that the weight should be at the middle. That's the implication, basically, right? So the uniform plate has a weight of 500 kilonewton. So yeah, in this case, if you see the diagram, it doesn't give you the point of G, the center of gravity. Why? Because it already informed that it is a uniform plate, and you should be able to understand that it is at the middle. If the question gives you G, then normally it will not give you uniform plate or etc. Right? You just use that center of gravity to determine where the force of the weight is acting. Right? So, okay, the uniform plate has a weight of 500 kilonewton, supported by 3 cables, and you can see there's 3 cables that goes to point A, point B, and point C, right? Find the tension in each of the supporting cables, right? So what you need to do here is you need to find what is tension in A, tension towards B, tension towards C, right? So the question is quite straightforward. Alright, so let's go and solve this problem. Now, for this one, actually there's only 3 unknown, as you can see there, right? 3 unknown. However, you have 6 equation, right? But actually for this particular question, some of the equation is not useful to solve this problem, right? For example, summation of fx is not useful because you do the summation of fx equal to 0 is simply just 0 equal to 0, right? Because there's no force in 0. Summation of fy equal to 0 is also not useful because it's just 0 equal to 0. And another one is actually moment about z-axis, right? If you do summation moment about z-axis equal to 0, then it's just 0 equal to 0, right? Because there's no more force that produces any moment about z, right? So you actually have 3 equations left, which is summation of fz equal to 0, and hence there you have 3 unknown, as you can see. If you do summation of fz equal to 0, 3 unknown. If you do summation of mx equal to 0, then you will have 2 unknown, right? And if you do summation of my equal to 0, you have also 2 unknown, right? So you have 3 equations, 3 unknown you can solve, right? So that's normally what you can do, right? So let me just redraw the equation there, x, y, and z, right? So basically, what are the forces? If you draw the free body diagram, so this will be basically a plate. Yeah. Now, even though this question is very easy, where you can straight away solve without even drawing the free body diagram, but remember, free body diagram is one of the learning outcome that we want to test. Hence, there's a significant marks there. So if you fail to draw the free body diagram, you still lose marks even though you can get to the answer of this question, right? Because the answer scheme and the marking scheme actually include Freebody Diagram to have a significant weight of the mark there, right? So make sure you draw the Freebody Diagram. Alright, so basically the three cables have the three forces there, right? So there's 1, there's 2, and there's 3 there. Also you have force going down here, right? And also you have the weight of the plate given, right? So it should be at the middle there, right? So if you just label this one is 200 kilonewton, and the weight is 500 kilonewton, and then you just label this FA, maybe FB, and FC. And then you have to also put the dimension. So this is 2 meter, 2 meter. So what it's, if you consider this one, is basically this is 1.5 meter, right? Of course, this is 3 meter, right? So basically, all the dimensions are there. Obviously, this also is 2 meter. Now, what is your option, right? So one is, well, if you see in the way, everything will be, meaning you have to solve using simultaneous equation. For example, if you do summation of fz equal to 0, you'll have fa plus fb plus fc minus 500 minus 200 equal to 0. Yeah, that's one equation. Then if you do summation of moment about x-axis, summation of moment about x-axis equal to 0. So FA produce counterclockwise, so FA a distance of 3, and then FC is also counterclockwise, so plus FC a distance also 3. This 200 Newton is clockwise, so minus 200 a distance of 3. This 500 is also clockwise, so minus 500 distance of 1.5 equal to 0. Right? And then if you do summation of moment about y-axis equal to 0, about this y-axis, so if you take if you take here, FB is clockwise, so minus FB a distance of 4. This FC is also clockwise, so minus FC distance of 4. This 500 is counterclockwise, so plus 500 distance of 2, and then this 200 is also clockwise, so plus 200 distance of 2. Right? So as you can see here, here is FAFC, here FBFC, here is FAFBFC. So it's 3 equation, 3 unknown. You can solve simultaneous equation, right? So that's one way to do it, right? Normally, I personally will not select this equation here, right? Because you actually have to do simultaneous equation, right? I'm normally quite lazy. I prefer, if there's any way not to do simultaneous equation, I will do it. Hence, I will do it differently, right? So that's just me. It's just because I'm that lazy. So I'll normally choose a different way, right? So as we mentioned earlier, when we say about the moment about x-axis, y-axis, and z-axis, you can actually create an axis, a parallel axis to x-axis, and use that one, right? So for example, if I use this one, right? If I create this x prime axis, right? Now, if you do this, then you have to introduce a new axis, right? Because x-axis is already given in the question. You cannot use x-axis somewhere else. So x-axis is already here. That's from the question. You cannot change it. So I don't want to use mx. I want to use mx prime. So I'll introduce an axis here. It should be clearly in your Freebody diagram if you want to do this. And then I'll just use, then summation of mx prime equal to 0. This is moment about x prime. Why do I do this? because I'm lazy, of course. But why can it solve? Because if you do axis here, this two unknown is on the axis, so it doesn't produce any moment. Hence, there's only one unknown there, right? So you can see that moment about x prime. So fb here is going to be clockwise about this x prime. So I will have minus fb times the distance of 3. Of course, all of these three forces doesn't produce any moment here. This 500 is counterclockwise, so plus 500, and the distance here is 1.5, should be equal to 0. Right? That's the only two forces that produce any moment about this x prime axis. Right? So here the calculation will be easy. So you can see FB is just 500, 1.5 over 3. So FB is straight away 250. This is kilonewton, right? So as you can see, it give you straight away answers there, and just to verify the answer, right? So it's 250 kilonewton, right? So as you can see, it's shorter, right? And it suits those lazy person like me, right? But I'm just showing here for you to see that there are alternative ways to calculate to get to the same answer. Now you can verify from the previous simultaneous equation, you should get the same answer anyway, right? So yeah. Now next, again, I'll create another axis if I want to. For example, here y prime, right? So I create y prime axis there. So if I take summation of m y prime axis equal to 0, so the only unknown that's relevant is here, right? FA, right? So because these two unknown is okay. Right now it's already known, FB, right? But earlier, if I want to start here, then this is still unknown. Then it's out of the equation there, right? So basically here, FA becomes, this one is producing counterclockwise about y prime. So we have FA is a distance of 4, and then this one is clockwise and clockwise. So minus 500, a distance of from that one is 2, and then minus 200, a distance of 2 equal to 0, right? So from here, basically you have FA equal to, this one is 1000 plus this one becomes 400, and then divide by 4, right? You bring it that way. So this is actually 1000, this is 400 divided by 4. So FA equal to, what is it? 1400 divided by 4, 114,700, 350, right? 350 kilometer. Right? After having solved this one, then if you go back to summation of z equal to 0, so basically you have FA, which is this one, already known, 350. FB is already known, plus 250. FC is still not known, plus FC, minus 500, minus 200 equal to 0. Right? This is still in the frame. Alright. It's still in the frame, right? That's 0. Right. So basically what is this? So FC becomes, what is that? So 700 minus 3, 4, 5, 600, is it? So FC equal to, is it 100? 100 kilometer? Yep. FC is 100 kilometer. So and because I didn't show the simultaneous equation, what will it be? You can verify for that yourself, right? I've shown the steps, but it should give you the same answer. And again, I'm too lazy to go through the simultaneous equation if I don't need to, right? So that's why I use this way, right? So yeah, so this is also okay. The focusing is a bit problematic right now. Can you still see? Hopefully you can still see. Alright, so that's how you can solve this problem. First, drawing the Freebody diagram. In this case, it's quite straightforward. Just replace the tension with the cable. Do not forget about the the weight itself. Alright, that's number one. And then number two, just select the equation accordingly and solve. And you can solve the unknown, right? Right. So this example 2 is completed. So I think there's another example, I think, right? So there's a group problem solving. If you see the slide, it's group problem solving. Right. So I think I'll just show the diagram here while I'm erasing, and we'll discuss on this one straight after this. All right. Okay, so if you see the diagram, this one is a bit more complicated, I think, for me to actually draw, right? So you have the pipe there from A, B, C, right? And okay, so the interesting point here is that this question is actually saying something about properly aligned, right? As you can see, okay, let's go before the question first, right? If you just look at the diagram, the question says a bent rod is supported by smooth journal at A, B, and C, right? So meaning that at A, B, and C is a journal bearing, right? So that's number one, right? Hopefully you still remember what is a journal bearing. So just by that, before we go further in the question, what's the implication? If you just imagine, if you draw the Freebody diagram, how or what support action do you have at A, B, and C, right? So just imagine for a while. I'll just give you some time to think. Alright, what is at A? Do you have AX? You should, right? Do you have AY? No, there's no AY, right? Do you have AZ? Yes, you have. Do you have MAX? You should have, right? Do you have MAY? No, you don't. Do you have MAZ? Yes, you have, right? So you have 4 unknown there. Now, if you go at point B, right, where you have the journal bearing, at point B, do you have BX? You shouldn't have. There's no BX because it freely move in BX. Do you have BY? Yes, you have. Do you have BZ? Yes, you have. Do you have MAX? No, MBX. No, you don't, right? Because it's free to rotate about X. Do you have MBY? Yes, you have. Do you have MBZ? Yes, you have. And then what about point C? Right? Do you have CX? Yes, you will have. Do you have CY? Yes, you will have. Do you have CZ? No, it's free to move, right? So you do not have CZ. Do you have MCX? Yes, you will have. MCY? Yes. MCZ? No, right? Because it's free to rotate about Z. So that's normally from our understanding of journal bearing, that's how it should be originally is, right? However, the question says, of course, F is 800 Newton, so the question actually gives the value for F. That force F there in the diagram is not having a value, but the question says F is 800 Newton. Assume the rod is properly aligned. So this is where the understanding that we actually skip about properly aligned comes into the picture. Now, yet again, as I mentioned, we how to say, I'm not sure in terms of the exam because it depends on the semester, right? But the understanding of I hope you roughly understand still what the example that I show, right? When you restrict the movement, it already restrict the rotation tendency, so the moment is not triggered, right? So in that case, all the moment that we mentioned about at point A, B, and C will be 0, right? That's the implication of properly aligned. Because why is this important? If we can't count the number of unknowns we just mentioned just now, right? At A you have 4, at B you have 4, at C you have 4. you already have 12 unknown and you cannot solve, right? So in this question, the only way to solve is if it says it is properly aligned. When it is properly aligned, at A you only have 2, which is AX and AZ. At B you only have 2, which is BY and BZ. At C you only have 2, which is CX and CY, right? All the moment is already equal to 0 because it is properly aligned, right? And if you do not understand that, you can ask in the comments or in the class, or go back and to my example of what is happening when we say it's properly aligned, right? Where the bearing actually can resist the moment, but it is not triggered because the bearing elsewhere already prevent from that movement that will never allow for that rotation anyway, right? So that moment is equal to 0. So that's basically it. Alright, so we'll go straight and I will draw the free body diagram so that we can answer this question, because the question is find the support direction at all the support, meaning at A, at B and at C. Alright, so we'll draw the free body diagram. So if you go to the axis, we'll have x-axis, y-axis and z-axis there. Oops. So the rod is basically from the negative y there. So we have, I'll use the red color. So the rod starts here, going here, and then going along the negative x-axis here, and then it actually goes up here, right? So basically that's how it is roughly, the rod. You still have to, again you have to draw the free body diagram in your exam, so at least something that you can understand to relate to the actual rod from the question, then it's fine, right? Alright, so there's the rod where you have point A here, point B in the middle here, this is point C, right? So you will have all the forces. So at point A there you will have AX and AZ, right? We have discussed this just now. At B you will have BY and BZ, and at C you will have CX and CY, right? And as you can see, I assume everything to be in positive direction. AX, AZ, BY, BZ, CX, CY all in the positive, so that whenever I get a negative answer, it's straightway understood to be in the negative axis direction, right? Also we have this force here, right? So when the angle is basically, right, you have, what is this? This is 30 degrees, and then going down 60 degrees, and this is F. The question says this is 800 Newton. So that's basically my free body diagram, right? If this is not clear, the angle, just see the diagram, the original diagram, right? It's harder to use to draw, right? What is missing? The dimensions. So this is 2 meter. What else? This is 1 meter. This is 0.75 meter. Going up is 2 meter. Right. So that's all the information that you should give in your free body diagram. Right. How many unknown? 6 unknown. So you will use all the 6 equations, obviously. Again, which equation to use first? Sometimes the question will leave you to use simultaneous equation anyway, right? This might be it, for example, right? For example, if I ask, what is, if you do summation of fx, how many unknown? You can say this x component, x component, 2 unknown, right? So it will not give you a straight answer. Summation of fy equal to 0, you have 2y component. Summation of fz equal to 0, you have 2z component, right? If you take summation of moment about x-axis, if you take this is x-axis, how many unknown do you have that create moment about x? You have 1 here, You have 1 here, 2 unknown. Summation of my equal to 0, you have 1 here and 1 here. Right? Summation of fz moment z equal to 0, you have this one and this one, right? So any equation that you choose basically will give you 2 unknown in that equation, right? So basically in this case you cannot run away from simultaneous equation even if you are lazy like I am, right? So to know which one that we can solve first, meaning simultaneous equation wise, you might need to list all the equation first, and then from there you see which can be combined with which to solve, right? So let's go then. So if you do summation of fx equal to 0, then obviously you have ax. Okay, it might be easier for you to write this in Cartesian vector form straight away, so that you can straight away see what is the x component, y component, z component. It's not compulsory, but to me it's easier to avoid any mistake and missing out on the component, right? So this one, in terms of vector form, based on this, you have x component is 800 cos 60 degrees cos 30 degrees I, and then that's positive, right? And then plus 800 cos 60 degrees sine 30 degrees j, and then minus 800 sine 60 degrees k. So that's the Cartesian vector of this force by using these two triangles, right? Alright, so again, going back here because I forgot to do that one first. So because this is having x component, y component, and z component, of course. So you have ax, you have plus cx, and then plus 800 cos 60 cos 30 degrees equal to 0, right? So that's the first equation. You have 2 unknown there. Summation of fy equal to 0, then you have by plus cy plus 800 cos 60 sine 30 degrees equal to 0, right? And then if you do summation of fz equal to 0, you have az plus bz minus 800 sine 60 degrees equal to 0, right? So far there's no how to say, because every unknown is already only mentioned once, right? Here, so you cannot solve anything yet. You have to combine with the moment equation. So summation of moment about x-axis equal to 0, right? So about this x-axis. So az doesn't produce any moment about x. Ax doesn't produce any moment, but az produces a moment about x. It produces clockwise. So minus az a distance of 2. This one is at origin doesn't produce any moment about x. By bz goes to this x-axis, no moment. Cy, it actually produces moment about x, right? Produce clockwise. So minus cy time distance of 2 equal to 0, right? Because cx doesn't produce any moment about x. So you have that one. And then summation of moment about y-axis equal to 0. Okay. So moment about y-axis equal to 0, right? So these two obviously is on the y-axis, so it doesn't produce any moment. This one at origin doesn't produce any moment. By parallel doesn't produce any moment. Bz, it produces counterclockwise. So plus bz times the distance of 1 meter there. And then about y, cy parallel, cx counterclockwise, so plus cx a distance of 2 equal to 0, right? You have to check sometimes, right? Because sometimes the distance, if you make a mistake, then it will affect everything, right? So ms here, just to check, az is to this two perpendicular, cy with respect to x is 2 also, bz with respect to y is 1, cx with respect to y is 2. And then summation of z equal to 0. So ax does produce a counterclockwise. So ax counterclockwise positive times distance of 2. Az is parallel, no moment. This one goes through the origin, no moment about z. by produce a clockwise moment, so minus by times the distance of what is that, 1 meter. Bz is parallel, no moment. Cy that produce clockwise about z, so minus cy times the distance of what is that, times the distance of 1.75. Cx, it actually goes through z-axis, so no moment, so this one equal to 0. So as you can see here, you have 6 equations, 6 unknown, and there's no way to escape free body diagram, not free body diagram, simultaneous equation in this case, right? Okay, let me check. Right, so basically you have to solve this simultaneous equation and you will get the answer, right? So if you want to check, basically I'll just read the answer and you can check later on, right? So ax is 400 Newton, az is 800 Newton, by is 600 Newton, bz is minus 107 Newton, minus 107, meaning it's 107 in the negative z direction is downward. Cx is 53.6 Newton, cy is 800 Newton. Right? If you want to check, those are the values. Please do try and please do check. Right? Why is it not focusing? Right. Attention quiz. This one, you just look at the slide, right? There's a triangle plate there. So it is supported by ball and socket joint at A, a roller joint at B, and a cable at C. Right? So how many unknown support reaction are there? Right? So hopefully you understand by now, right? So a cable is just one unknown tension. A roller is just one unknown, which is normal, and ball and socket you should have x, y, z forces. It doesn't restrict any moment, right? So hopefully you know that one and you can answer that one. Yeah. So that's it for this lecture, right? Please do try, right? And again, while we are establishing all of this, you might notice, right? All of this positive and negative, it is from you be able to visualize whether it's clockwise, counterclockwise, right? So that's important because this is clockwise or counterclockwise about x-axis, about y-axis, about z-axis. You have to be able to visualize. Now, can this be solved by using r cross f? Yes, it can. Right? For example, r cross f at A, r cross f at B, r cross f at C. And you'll get basically the same equation in the end as you get here. Basically here, right? R cross f is the moment part, right? So you get these three equations when you separate the I component, Z component, I, J, and K component, right? You can try if you want to do that and verify. It should be the same. Alright, so I think that's it because the slide is until that point. The rest, we will cover the rest in the lecture. Meaning the rest of the example, right? So if you want to see more problem getting solved, especially in 3D, watch the recording of the lecture. If you are my student and you are in the lecture, you actually have gone through that one. If you are not my student, go to that lecture where we cover chapter 5 on 3D problems, solving other problems. Yeah. So that's it for this recording, alhamdulillah. So we are at the end of chapter 5. So just to recap, chapter 5 is just about equilibrium of rigid body, 2D and 3D. The new thing here is how to draw the free body diagram considering all of the support, different type of support that provide different type of support reaction, force and moment, right? So make sure you know how to draw the free body diagram properly. Make sure you actually draw the free body diagram in the exam with all the forces, with all the moments, and with all of the dimensions. And make sure you know how to use equation of equilibrium to solve the problem. Wallahu alam. So we end here. Subhanakallahumma bihamdik, ashhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik. Wassalamu alaikum warahmatullahi wabarakatuh.